Okay, I'm moving right along. This is still Monday for me. You guys are a few days later. I'm in the zone, so I'm just going to keep recording these videos. We are going to go through how to solve conditional projectile motion problems. So this is another step of like intensity above what we were just working on. So for conditional projectile motion problems, we have something that we have to, like a goal that we have to meet essentially. So we're going to look at this problem. A tennis player strikes the tennis ball with an initial velocity of 4.7 meters per second horizontally. The ball is initially 1.28 meters above the ground and 12.9 meters from the 0.914 meter tall net. Does the tennis ball make it over the net? So we have to meet the condition that we are going over a 0.914 meter tall net that is 12.9 meters away, knowing what we know. So here's a diagram of what's going on. This person is just hitting the ball horizontally, so there is no velocity going on in the y, just acceleration due to gravity. We know how high the initial velocity is starting, and we know that 12.9 meters later in the x, we still need to be at least above 0.914 meters. So how do we go about figuring this out? Well, we can put our variables into our horizontal and vertical columns. So we know our horizontal variables are 12.9 meters is how far we're trying to go. And in the x, we have a velocity of 44.7 meters per second. Now in the y, we could either say our displacement is that negative 1.28 because that's how high we start. So like that's how far it can fall, or that it can only fall 0.366 meters and still make it over that net. So we have no clue which one of those we're supposed to use in the y. We have an initial velocity in the y of 0 because we're hitting the ball perfectly horizontally. So we don't know what our final velocity is. And our acceleration is due to gravity at negative 9.8 meters per second squared. We don't know our time. So we have a lot of information that we have to make sure we put in the right place. So if we use the 12.9 meter value for the range, we can't also assume that the tennis ball is going to be at 0.914 meters, which would make that displacement how far it can fall, so that negative 0.366. We can't assume that we are hitting both of those things at the same time. We can't know that that's where the tennis ball is going to be. We have to solve for where the tennis ball is going to be. So we're following the path of a parabola. The easiest thing to do is to determine how long it takes the tennis ball to reach the net horizontally, so at 12.9 meters, and that's going to give us our time. Then we have to figure out what the height is going to be at that time. And usually in math, you'd see it as like the height is a variable of time, so h parentheses t. And it's kind of the same idea as checking to see if a point is actually on the line of a parabola or not. So if it's going to take t seconds to travel to the net, we just have to see what the vertical displacement is after those t seconds. And if it's dropped more than that 0.366 meters from where it started, then it is not going to make it. So just to visually, for visual people, because I'm one of them, we're going to see how long it takes to get here and double check how far we have fallen, which will be a negative displacement here. So if this number is greater than negative 0.366, then we did not make it over the net because it's going to have fallen farther and it'll bump into the net and not go over. Those are the words I'm trying to say. Okay, so this is just that example written out. And again, so does the tennis ball make it over the net? We have our diagram completely drawn out. We see all the variables that are listed. We need to figure out how far we have fallen on that parabola after we've gone 12.9 meters in the x. So, filling my variables in, like I showed before, there's a lot that we can solve for. Time is going to be the first thing that we want to solve for. And thankfully, because we have two variables in the x, we can use our simple equation, where our velocity in the x is our displacement in the x divided by time. So I know what my displacement is because we're moving at 12.9 meters to get to the net. And I know my starting velocity, and the x is 44.7. So it takes me 2.8859 seconds to reach the position of the net. So this is one of those examples where we're saying, like, hold on to as many decimal points as possible so that you get a really accurate reading, because obviously we're reading out our height 3 decimal places out. So we want to make sure that whatever we're calculating gets us close enough to understanding what's getting there. So whether you write it out and use that every time you type into your calculator, or you pull from the memory in your calculator, either way, using more decimals is going to get you the more accurate result, and it could be the difference in the answer being yes or no. So then we're going to use our vertical displacement because now we've solved for our time. Ooh, there's some numbers that are all wonky there at the bottom of the slide. So my initial velocity in the y is 0, so that's why we canceled that out there. And then I have my acceleration, and then my time was at 0.28859. So they kind of solved it weirdly in steps. So in case you can't read it, the displacement in the y is negative 0.408 meters. So in that time frame, I've dropped 4.08 meters. So do I make it over the net? What it's telling me is I start here and I subtract the displacement in the y that I just calculated. The ball is going to hit at 0.87 meters above the ground, which is like here. So the ball did not make it over the net. So we could also have done this with vertical variables. So we could just say, okay, we need to find out how long it's going to take for the ball to fall, that 0.366 meters, and then solve for time. But because time is our easiest variable to solve for, this is probably the way you'd want to go most of the time. But you could go the other direction as well, and you should end up with a very similar answer as long as you get no. The math that gets you there, I will look at. So if the value for the range in that case is greater than 12.9 meters, so if you solve for the vertical and how long it took to fall, if it took longer than 12.9 meters to fall, that means that it was over the net by the time it fell below that net height. And if it was less, that means it fell sooner. So it's more difficult and usually involves factoring, quadratic formula, which I know we all love, but not that much. So we can embrace this challenge and try it this way. So a cannon is located at the top of a 45-meter tall seaside fortress. An enemy ship is approaching in its bow, so the front of the ship, 750 meters away when the cannonball is launched at 135 meters per second at 8 degrees above the horizontal. Assume the ship is 32 meters long and moving toward a fortress at 2.85 meters per second. Does the cannonball hit the enemy ship? At a quick glance, I'm really excited because all of the units are in the right style, so I don't have to redo any of that. But it sounds really complicated. First thing, draw yourself a diagram. Hey, look, there's a diagram. So we've got a fortress. It's a cool fortress. I wish I had a fortress. And it's shooting a cannon at an enemy ship. Ooh. Boop. And it's 8 degrees above its horizontal at that turret, which is 45 meters above the sea level, which is where our ship is sitting, obviously. We have an initial velocity of 135 meters per second. We know that the ship is 750 meters away, and it's also 32 meters long. So as long as we hit the ship somewhere in that range, we should sink it, theoretically. I don't know, Pirates of the Caribbean kind of like, they got hit a lot and they didn't really ever sink. But we'll pretend. And the ship is moving towards us at 2.85 meters per second. So we have a lot of different ways that this can go. We can end up short, just a little short, / maybe hitting the very front of it as it's moving, or we go too long. So we've got a lot to figure out here. So I'm going to calculate my components of my initial velocity. So going back and looking at this triangle right here, I have 135 meters per second and 8 degrees. So here's my y and my x. So the velocity in my x is going to be cosine of 8 degrees times 135. And the velocity in my y is going to be sine of 8 degrees times 135. So solving for those components, I get 133.69 meters per second heading in the x. And in my y, I'm going 18.79 meters per second. So now I'm going to write that into my table for horizontal and vertical variables. This is the table that I am going to be looking for when you solve all of your equations, because this is the table we're trying to fill in. We want to know all these things. There's a lot of variables. This is the easiest and best way to keep it organized. And when in doubt, I can always look back here to try to find your answers if you forget to box it in. So I know my velocity in my x, my velocity in my y. I know that the cannonball is going to have to drop 45 meters from where it started. So my displacement in my y is 45 meters. And my acceleration due to gravity is negative 9.8. So what do I solve for next? I have 3 different variables that I could go for. So I'm going to go ahead and calculate for a time. So I start with my equation that only includes my initial velocity. And I'm going to plug in that I know it's going to fall 45 meters from where it starts. We calculated my initial velocity in the y. Should have a y next to it. And then I have my acceleration due to gravity. Plug all that in, rearrange it into my quadratic formula. So I have my a, b, and c. Then when I do that, I can plug it in. Negative b plus or minus the square root of b squared minus 4ac all over 2a. It's a very useful equation. This song is very helpful. So when I solve for that, I'm going to get 2 different numbers. Remember, we don't do negative time. Inadmissible feels like a really big word. We just don't use it. We can't do time negative. I've been watching Umbrella Academy, and they move backwards in time a lot, and I just kind of sigh every time. It's funny. I crack myself up. Anyway, so I'm going to use 5.5 seconds as my change in time. So it takes 5.5 seconds for that cannonball to strike the water with that initial velocity and that launch angle. So now, when I do that, if I've got my 5.5 seconds, I come back to this guy right here. So 5.5 seconds. And both of these, my horizontal component is the easiest thing to solve for. So that's what I'm going to do next. So my velocity in the x equals my displacement in the x over my total change in time. I plug in what I know after rearranging it. I know it's going to take 5.5 seconds. And I'm heading at 133.69 meters. So I'm going 735.259 meters in the x direction. So that's pretty big, right? Like, how far away is my ship? Oh, but is it close enough? 750, and then we've got 32. So now we're going 735. Are we going to get there? We have to figure out where the ship's actually going to be. So the ship's moving at a constant velocity. It's not slowing down. It's not speeding up. So we can use the exact same equation because, yay, constant velocity. I don't know why I'm writing all this out. I just said it. Anyway. So I know that I started 750 meters out in the positive direction. And then I have to figure out, okay, so I'm heading 2.85 meters per second closer to the fortress over a period of 5.5 seconds. So what I did here is I just snuck in my starting position. And then I added the motion into it. So after that 5.5 seconds that the cannonball was in the air, I am now at 734.325 meters away from the fortress. So I'm 734.3 meters out from the fortress to the front of my ship. My cannonball went 735.3 essentially into my 32-meter ship. So I have been hit. Now it's near the front. If my front is high enough, I might not get that much damage. May not hit the sails. Probably can't retreat because look, I still have 30 meters left essentially on my ship. And I'm moving. You can't just stop a ship on a dime and turn it around. So not looking too good for the pirates. So that's how we solve conditional problems. We have to look at the information that they're giving to us and what's happening along the way and try to piece together the equations that we have. So using your 5 kinematic equations and then your simple ones like your velocity is your displacement divided by time. Those are going to be like the key elements to figure out what's going on and filling in your horizontal and your vertical components. If you have questions, I'm here.